have a look today at proof by induction. This is your starter. Prove that the sum of the sequence 1, 3, 5 all the way to the nth term Tn equals Tn minus 1. Prove that that sum is equal to n squared. Now, I'm not sure why I have a guy and his brain is filled with fruit and vegetables. So we're going to ignore that for now. You're going to do the starter question. Maybe you can use the sum of an arithmetic or geometric sequence to help you. And we're going to go through it together. So pause the video, have a go, come back. Once you've had a go, let's see what happens. So what is the sum of this sequence? For me to know, first I have to decide, is it arithmetic, is it geometric, or is it neither? Let's look. Our first term, a equals 1. Now, we notice that going up, I'm actually just plussing by 2 every time. So my difference is 2. Now, this term here, I'm not sure what number term it is, so I'm just going to label it as t of n. It's some number term in the sequence, I just don't know where. Now, this is arithmetic, right? So I know the sum formula for an arithmetic sequence would be n over 2, and hopefully remember 2a plus n minus 1 times the difference. I don't know what n is, but I do know what a and d is, so let's sub that in. N over 2, well, a is just 1, plus, not sure what n minus 1 is yet, and the difference is 2. Let's expand and simplify. On the inside, I'll get 2 plus 2n minus 2. Okay, some things will cancel. The negative 2, the positive 2, n over 2 brackets 2n. These 2's will also cancel, and I'll be left with n squared. So therefore, the sum is n squared. And we've proven it using the formula. But this is fine, except we run into some problems. One, what if you didn't know the sum or the series formula for an arithmetic sequence, right? We'd be in trouble for proving this. The next thing is, what happens if the sequence wasn't geometric, wasn't arithmetic, and I didn't know a formula to use? That means we need a different way to prove the above statement. So we're going to use proof by induction. Proof by induction, we use whole numbers, normally natural numbers as well. And there's a very specific recipe which must be followed called the CAPE method. Here are the steps. First step, we check that the statement is true for the smallest possible value of n. So for the first number in our sequence, or for the smallest possible integer that we can use for that statement. The second thing is, we're just going to assume that it is true. So we're just going to assume it's true for the general case for n equals k, so any number k. Then we have to prove the statement is true for the next term in the sequence. So we prove it's true for n equals k plus 1, and we use the step above to help us. That way, really the theory goes that if you prove for the smallest number, and then you've proved it true for the number plus 1 after that, and the number after that, or the term after that, and after that, and after that, then you can kind of say, well, if it's true for the first term and all the ones after that, then by induction, it's probably going to be true for every single number in our sequence or our statement. So lastly, we explain our conclusion using a pretty specific, sentence that by induction, and we've followed the recipe, that our statement must be true for all values of n that work. We use this method for summation, for problems involving divisibility and inequalities. And here is our little cape, so hopefully it's a little clearer why I got you to colour in the picture in the first place. We're going to prove that the sum of this sequence, the one we had in the beginning, using proof by induction. So first, let's just note out exactly what we're trying to prove. So we are trying to prove that 1 plus 3 plus 5 plus all of the way to our nth term, Tn minus 1, equals n squared. So I'm going to call this the left-hand side of my statement and this part the right-hand side. And I've got to prove that these two things are equal. Let's start with step 1. So we don't prove, we check it's true for the smallest value of n. So what is the smallest number of terms you can have in any sequence? Just 1. So we're going to prove it's true if we only had the first term in our sequence. Let's start with the left-hand side. So basically we're just trying to prove that the left-hand side is equal to the right-hand side. So what is the sum of the first term looking at our left-hand side? Well, the first term is just 1. So the sum of 1 is just 1. Then we look at our right-hand side. If we're using n equals 1, what is n squared? Well, that's just 1 squared equals 1. Now notice the left-hand side and the right-hand side are both the same. Therefore, this statement is true for n equals 1, our smallest integer. If you got on the left-hand side a 2 and the right-hand side say 6, then we couldn't do this step, and the statement's probably not true for anything. So, second step, assume true for a general case. So we call that number n equals k. Then when we do this, we're just going to substitute everywhere you see an n, put a k instead. So we're saying that this is true. 1 plus 3 plus 5 plus all the way to, this time I write k minus 1 is equal to, again, sub the k in, k squared. So I'm going to say this is true. The third step is now I have to prove it's true for the next term in our sequence. So the k plus 1 term. So what we do with the left-hand side, again, we take it separately because we're trying to prove. So what would the left-hand side look like if I added an extra term onto the end? I would still have 1 plus 3 plus 5 plus all the way to 2k minus 1. But I'd have an extra term, right? The k plus 1 term. So this time, everywhere I see a k, I'm going to put k plus 1. But make sure you put the brackets around. So this is my series if I added an extra term. Let's just maybe simplify the brackets there a little bit. So I'd get 2k plus 2 minus 1. That's just going to be 2k plus 1. So I'm going to have to show that this is true to my right-hand side. So my right-hand side now, instead of having a k, we're going to put in k plus 1 instead. So for the next term on. And your job, or our job, is to say that the left-hand side is definitely equal to the right-hand side, and we use the step above. So notice the step above, we said 1 plus 3 plus 5 all the way to 2k minus 1 is equal to k squared. We said that's definitely the case. So I'm going to start with my left-hand side on step 3. And I'm going to say, okay, well, I know this is equal to k squared from step 2. So then on my left-hand side, I have k squared now plus 2k plus 1. Can we manipulate this left-hand side so it looks like my right side, k plus 1 all squared? Let's try it. I'm just going to move this part up over here so we're still looking at the left-hand side. Let's expand the left-hand side, bring the terms together. I would get k squared plus 2k plus 1. And what do you know it? This is k plus 1 all squared, which is equal to my right-hand side. So therefore, I've proven the left-hand side looks like the right-hand side. So So I say, therefore, left-hand side equals right-hand side. The statement is true for n equals k plus 1. My last step, step 4, is to write your conclusion. So because we've proved it's true for, or checked it's true for n equals 1, and I've shown it's true for the next term onwards, my k plus 1, and every k plus 1 after that, it's going to be true for all n's that we can use here. So therefore we say, by induction, the statement is true for n equals 1, and then the next term would be n equals 2, the next term n equals 3, and so on. Therefore, true for all n. Right, warm up one, first one out of the way and over and done with. Let's apply it to another question. Here's the next question. Prove that by induction, this time our sum is a little uglier, a lot of squares going on here. 1 squared plus 2 squared plus 3 squared all the way up to n squared is equal to n bracket n plus 1 bracket 2n plus 1 all over 6. Let's use our steps. So I'm going to write, this is what we're trying to prove here. Then we're going to check true for the first term. And our first term is 1 squared. So for n equals 1 brackets the first term. So if we only had one term on the left-hand side, okay, then what is the sum of the first term? 1 squared. Well, 1 squared plus nothing is just 1. The right-hand side, okay, this one we have to plug some things in. So everywhere you see an n, you're going to put a 1 instead. So I'd get 1 brackets 1 plus 1 brackets 2 times 1 plus 1 all over 6. Well, that is equal to 1 times 2 times 3 divided by 6. 1 times 2 times 3 is 6 divided by 6. That indeed equals 1. Left-hand side equals right-hand side. So therefore true for our first term, n equals 1. Second step, we're going to assume true for n equals k. Best step of all. Okay, so where I see k on the left-hand side, just put it on the right-hand side, just put it as well. So we're going to assume this is true. All the way to k squared is equal to k bracket k plus 1, 2k plus 1 over 6. Third step, I'm going to run out of room soon, so I might need to swap slides. We're going to prove true for n for the k plus 1 term, so n equals k plus 1, and I'm just going to say we always use step 2 here to help us. So let's have a look. What would the left-hand side look like and the right-hand side look like if we plus an extra term to the left-hand side? So left-hand side, what are you going to be? 1 squared plus 2 squared plus 3 squared plus all the way to k squared plus, if we added on the extra term, that would just have, where you see the n, put a k plus 1 squared. So that's our extra term. On the right-hand side, what will we have? Well, we were going to have, every time we put an n, we're going to put a k plus 1 instead. So it'd have k plus 1. Just be careful of the brackets. n plus 1 will become k plus 1 plus 1. Then we'd have a 2. Remember, n is k plus 1, so keep that in the brackets, plus a 1 all over 6. Now, I'm just going to simplify the right-hand side a little bit. So I'd have k plus 1, k plus 2, and then this last bracket would become 2k plus 2 plus 1, so 2k plus 3, all over 6. Now our job is to show that the left-hand side can be written in the same form as the right-hand side. Okay, so I've just created a new slide here. So let's manipulate the left-hand side, try and make it look like that fraction on the right. So always use step 2. So from step 2, I know 1 squared plus 2 squared all the way to k squared is equal to k plus 1, 2k plus 1 over 6. So let's substitute that in. I'm just going to leave my k plus 1 squared at the end, so don't forget that term as well. Okay, and I'm just going to work on the left-hand side only. Try and get in the form of the right-hand side. Now, it depends what you want to do here. So there are a few different ways. I'm going to put everything over 6 because my fraction on the right-hand side is everything over 6. So I'd have k plus 1, 2k plus 1, plus, I've got to times this side by 6, k plus 1 all squared, all over 6. Okay, it's looking closer, but not really exact. Notice how the first term has a k plus 1 squared. He also has a k plus 1. Sorry, both have k plus 1. I'm going to take that k plus 1 out the front. So I'd get something like k plus 1. In my brackets, I'd have k, 2k plus 1. And then this one was squared, so I'll still have a plus 6 and a k plus 1 here. Everything is still over 6. Now, I can try and simplify the inside of this bracket a little bit more. Let's see what we get. We get 2k squared plus k plus 6k plus 1 all over 6. Okay, and then maybe again we keep simplifying k plus 1. I would get 2k squared plus 7k plus 1 all over 6. Now notice the k plus 1 can stay the same. The 6 down the bottom can stay the same. But 2k squared plus 7k plus 1, if you factorize it, guess what it's going to factorize into? You've got it. 2k plus 3 and k plus 1. So you can do that by doing 2 times 1 is just 2. Two things that add up to 2. And then sum to give you 7. Well, that could be a 3k and a 4k. And you expand it and you factorize like normal. So step 4. Well, before that, I say left-hand side equals right-hand side. Therefore, true for n equals k plus 1. And then I come to step 4. I'm just going to do that over here. Therefore, by induction, this statement is true for n equals 1, our smallest value, and then all the values after that. So n equals 2, n equals 3, and so on. And thus is true for all possible